Hello ladies and gentlemen, and welcome back to Prospect Charter School's Algebra 2 course. Today we're going over section 2.7, curve fitting with linear models. Now, when it comes to curve fitting with linear models, what we're going to be doing is we're going to be looking at a data plot or a scatter plot, and then trying to determine a line that best fits the data. To do that, we first have to know if the data would even be close to being correct with a line for something called correlation. So the first thing we're going to go over is correlation. Correlation is how closely the data matches. So how closely the data matches an equation. Now there are three different types of correlation. There is positive correlation, there is negative correlation, and then there is no correlation. So to give you an idea of what positive correlation is, first we're going to look at a graph, and then our data points are going to be in purple, and they're going to be looking something like this. If we look at it, it looks like that it's a line going from the bottom left to the top right. That would give us a positive correlation because it creates a positive slope. Well, what about negative? Well, once again, we're going to be looking at a graph, and all of these are going to be red, and it would look something like this. Notice how our data points kind of form a line going from the top left to the bottom right, giving you a negative slope. In that regard, it is a negative correlation. Now for no correlation, we're actually going to be given two examples, mainly because one of them is a very special case. The first one is going to have data that looks something like this. If you'll notice, it's everywhere. That means there's no correlation. There is no effect that the variable that we put on our x-axis has on where points are on the y-axis. This would be no correlation. Another version of this would be if all of our data points are in a straight flat line. This means that there's no correlation. X is having no effect on y. Y is remaining stagnant. It remains the same throughout, no matter how much you vary the x. So there is no correlation between them. If the y value data changes all the time, drastically, with every version of x, that tells us that there's absolutely no correlation and that y is very volatile. Versus on the second one, the y is very stagnant. All right? Cool beans. Let's go ahead and go on to some more stuff. Now, in correlations, we have something that is called the line of best fit. Line of best fit. This is the line that best fits the graph given our data. So for an example, if we saw a data set that looked something like this, and we wanted to create a line of best fit, I think the line of best fit would probably look something like this, where the data points are all really closely related to the line. And then I take 2 points on the line. It looks like this is 1 point at 1, 2, 3, 4, 5, 1. And then we'd have a second point, which I think would be up here at 2, 1, 2, 3. And then we would find the slope of the line using y2 minus y1 over x2 minus x1. By the way, what kind of correlation is this? Negative. Very good. And that means what kind of a slope are we going to have? Negative. Very good. All right, so we take our y2, which is 1, and we subtract our y1, which is 3, and we divide it by our x2, which is 5, minus our x1, which is 2, and we get negative 2 over 3. So the slope for this line of best fit would be at negative 2 over 3. And then using y is equal to mx plus b and the point 5, 1, I pick 5, 1 because it's like right on target. The 2, 3 can be off by a little bit, so like I said, I want it to be as perfect as possible. The 5, 1 is absolutely perfect, so I'm going to use it. So I plug in the y value for that, which is 1, and I put in the x or the m value, which is negative 2/3, and then I have my x value, which is 5, and then plus b, and then I solve for b. So to multiply a whole number by a fraction, you divide by the bottom number and multiply by the top. 5 and 3 have nothing in common, so we'll end up with 1 is equal to negative 10 over 3 plus b, and it looks like we're going to have a fraction for our y-intercept, which is fine. Add 10/3 to both sides, so we have 10/3 plus 3/3 is equal to b. Notice that I converted the 1 to 3 over 3. And then 10 plus 3 is 13, so we have 13 over 3 is equal to b, giving the line of best fit equation as y is equal to negative 2/3 x, negative 2/3 x plus 13 over 3. So that's how we find our line of best fit. First we find the slope, then we put it into the equation, and then the equation y equals mx plus b with one of the points on the line of best fit, and then we find our y-intercept. It is multiple steps, but I think we can get it down. So the line of best fit is the line that best fits the data. But now we have a question. How good or how well does this fit the data? To do that, we have something called the correlation coefficient. So I'm not going to teach you how to calculate the correlation coefficient because it is really complicated. That's like Stats 273 college level stuff. Not going to go there. Instead, you'll just be told what a correlation coefficient is and tell if it is really good or really bad. A correlation coefficient is a number between negative 1 and 1 that denotes how closely the equation fits the data. The further it is from 0, the better it fits the data. So, for an example, let's say that we are given that our R is equal to negative 0.5. R is the correlation coefficient, so that's the correlation coefficient. If the R is like negative 0.5, that means it kind of fits the data. It means that about 50% of the data points fit the data, and it's not very good. I would say that's a really bad correlation coefficient. But if I saw an R of 0.95, that would be really, really closely fits the data. So an example of each, if we're looking at R of negative 0.5, let's say that this is my line of best fit, then the data points would probably look something like this. Notice that all the data points are pretty far away from the line, but it does seem that you're having a negative slope to the line. Now, if we're looking at a correlation coefficient of 0.95, then our data set would probably look like this. With that as our line of best fit. Notice that almost all the data points touch the line, and if I had drawn the line correctly, let me try redrawing it. Notice that almost all of our data points are exactly on the line. If they're not on the line, they're off by just a tiny, tiny bit. So that would be a really, really close positive correlation. Just like this is a kind of loose negative correlation. Note that when the R or the correlation coefficient is negative, you end up with a negative slope. And if it's positive, you end up with a positive slope. And that, ladies and gentlemen, is the correlation coefficient. All right, other than that, we are going to go over one example with actual data as to how to find the line of best fit. Let's say that we are going to look at Dave's Deli sandwiches, and it gives us our number of grams of fat and then the number of calories for each sandwich. So let's say that we have our fat in grams, and we are comparing it to the calories. And when we're looking at our sandwiches, we have one that has 5, 9, 12, 15, 12, 10, 21, and 14. And then we look at the calories are 360, 455, 460, 420, 530, 375, 580, and 390. Now, we'll note that the number of fat grams are not in linear order. So what I'm going to do is I'm going to put them in order from least to greatest. So I'm going to call my fat grams X and my calories Y. And then I'm looking through it and I'm like, okay, what's the smallest number up here? 5. Okay, so we have 5 and its value, Y value is 360. And then after 5 comes 9 at 455. And then after 9 is 10 at 375. And then after 10 would be 11. There isn't one. Then there's 12. We have two 12s. Two 12 values. That's not good. It means it can't be a function, right? So one of them is at 460. The other one is at 530. Then we keep on going. After 12 is 14 at 390. And the last one would be 15 at 420. Now, is there a correlation between the number of grams of fat and the number of calories? Well, that's actually pretty easy to determine. 5 and 360, 9 and 455, it went up. And then from 9 to 10, it goes up. From 10 to 12, it goes up. At 12, it stays up. From 12 to 14, it goes down. But from 14 to 15, it goes up. So it's almost always going up. That means that there's definitely a correlation, and it's going to be a positive correlation. Now we need a line of best fit. Now for our line of best fit, we're first going to have to kind of semi-graph this, right? We're going to have 5, 10, 12, 14, and 15. So if I'm looking at this, it goes from 5 to 15, which would be 6 tick marks. 1, 2, 3, 4, 5, 6. And then I'm going from 360 to a maximum of 530. So I think going by 50, starting at 350 would probably be a good idea. So that'd be 350, 400, 450, 500. Okay, so starting at 350, going up to 500. And then the last one would be 550 at the very, very top. My pen will write today. Come on, write pen. There we go. And then across the bottom we start at 5 and we end at 15. So if we look at the first one, 5 is at 360, that's about here. 6, we don't have one. So 5, 6, 7, 8, 9. Okay, from 5 to 15, we're going by what, 2s? 1, 2, 3, 4, 5. Yeah, we're going by 2s. So to get to 9, that would be 2, 4. So at 9, we're at 455. So 354, 455. So about here. And then at 10, we'd be at 375. So that'd be about here. 354. Nope. Other side of the line here. 12 at 460, so that's 5, 6, 7, 8, 9, 10, 11. 12 at 460, so that's 354, 450, 460. 12 at 530. 14 at 390. And then 15 at 420. So there's our data. And if we look at it, it looks pretty awful. However, there should be two lines that are kind of standing out as where all the other lines are kind of being around. And that's these 2 points right here. If I was to draw a line of best fit, I would probably want it to go through those 2 points because then the data would be about equally distant from all of them. So what were these 2 points? These 2 points were at 5, 360 and then 12, 460. And then from there we can do our normal thing. We know what the slope is. That would be 460 minus 360 divided by 12 minus 5, which would give us, let's see, 100 over 7. And then we can find our b by plugging it in. Now, in the interest of saving time, we've already seen how to do this. We're just not going to go over it in class today. If you want to, feel free to look at your textbook. It will give you a few things. It will give you some good methods. It'll also teach you how to use your calculator to do a lot of this for you. Doing it by hand is very cumbersome and very time consuming, and I want to give you guys as much time as I can to do your homework. So we're just going to go ahead and move on to just that. It's time for your homework. So your homework is going to be probably really short, at least as the number of numbers. It's probably going to be a lot of work, so I'm not going to give you too many. So this is going to be section 2.7, and we're going to be looking at numbers 1, 3, 7, 9, 11, and 15. All right, there you go. You've got, what is that, 6 numbers to do? Some of them are really easy. 7 and 9, I think, or 9 and 11 are going to be like super easy. 2 of them are like super duper easy. The other 4 are going to require something very similar to this right here, but fortunately they already graph it for you, so it won't be too difficult. All right, good luck and have fun.